Moving to chapter 6 of your book, where we will consider the layout planning. In this chapter, we will talk about the main considerations in layout planning. We will learn the systematic layout planning and the steps of this approach. And we will follow the steps of this approach to design some layouts. We will also talk about construction and improvement type algorithms for layout planning. You will be, at the end of this chapter, you will also learn the ALDEP, CoreLab, and CRAFT algorithms as well. So let's get started. In layout planning, the first step is to identify the right number of departments to have, and also the types of the departments that you need to design, you need to include in your layout planning. After this step, you generate and evaluate a number of layout alternatives. So here, creativity is important. There are some methods to create layout alternatives, but there is no single unique way to do it. At the end, you need to use your judgment, you need to use your creativity. And the thing is, anyone that follows the same steps of, for example, systematic layout planning that we will talk, may end up with a different layout alternative. So the important thing here is not to come up with a single alternative, but to generate a number of layout alternatives, and from these to select the best one, or your final selection, your final layout design will be based on one of these alternatives. Okay? So what we will do is we will generate a number of layout alternatives. Either we will select one of those, or we will select one of those as our basis, and then we will modify it and come up with our final design. But the thing is, how many different layout alternatives should we generate? At this step, you need to use your judgment, because if you try to generate too many layout alternatives, then at the end, generating all of these, evaluating all of these will take a lot of time. Okay, so you need to generate a reasonable number of layout alternatives. Okay, but the question is, how to generate these layout alternatives? And in this chapter, in the following slides, we will be talking about some general steps, some different ideas, different methodologies to generate layout alternatives, and how to compare these alternatives with each other. When we talk about facility layouts, we should consider two levels. The first one of these is the block layout. Okay? The block layout is a rough cut, let's say, rough design of the layout. It shows the location, the shape, and size of each department. But the details of the layout is not included in block layout. You basically see the size of the department, the shape of the department, and the location of the department. Only the macro flows are concerned in block layout. But in the second level is the detailed layout, in which the exact location of all equipment, workbenches, storage areas within each department, every detail of the design is included, and it's concerned with microflows. Okay? So for the facility layout design to be complete and effective, both this block layout and the detailed layout need to be developed and evaluated carefully. There are a number of different methods, different techniques that can be used to develop layout alternatives. And basically, we can talk about two types of procedures. The first one is the construction method. So in construction method, what we do is basically there are no initial solutions in our hand. We start from scratch and we develop a new layout at the end of this phase. There are nothing initially in our hand. We start from scratch. We follow steps of the algorithm, and at the end we come up with a design. The second procedure, on the other hand, is so-called improvement. In these procedures, you start from an initial existing layout. Okay? You already have a layout, and by making changes, by making modifications on this layout, you try to improve it. Okay? So these are the two types of procedures in developing layout alternatives. We can talk about different layout procedures. One of these that we will talk will be the graph-based construction method. In the following slides, we will make examples of this method. Also, you can, if you like, you can read your book about the Apple's plant layout procedure. Basically, it identifies a number of steps that need not be followed in sequence, and by these steps you come up with a layout. Or again, in your book you can read about Reed's plant layout procedure. But mainly here we will talk about the graph-based construction method, and also we will talk about the systematic layout planning method of Muther. So this method is developed in 1973, and mainly it uses the activity relationship chart as the basis. And using this activity relationship charts, following a number of sequential steps, okay, so it generates first a block layout, and then from this block layout, it generates a detailed layout. Okay, we will be talking about this systematic layout planning in the following slides as well. Okay, let's talk about the graph-based construction method. So as the name implies, this is a construction method, and it means that this method generates a new layout. Okay, at the end of this method, starting from scratch, you will end up with a new layout. Basically, we can talk about three steps of this algorithm. The first step is to build a graph. Okay, what's a graph? A graph consists of a number of nodes and the number of edges connecting these nodes. In the following slides, you will see examples, and these graphs will represent the adjacency of the departments. Okay, if two nodes have an arc in between, have an edge in between, then the nodes will represent the departments, and the edge in between will represent if these departments will be adjacent in the layout or not. Then we will convert this graph into a block layout. It will be easy, but you will use your creativity during this step, because there may exist alternative layouts. And then we will evaluate these block layouts, these alternatives, and select the preferred alternative. Here usually adjacency based scoring will be used. So we will talk about this scoring later on, adjacency based scoring. Okay? So don't be confused at this time, but we will evaluate the final layout using this scoring. Maybe the most important step of this graph-based approach is the construction of the graph. So in this step, basically, we will start with selecting two departments. And which two departments? The two departments that have the largest weights in between. If there are more than a pair of such departments, more than one pair of departments which has the same largest weight, then we will select one of them randomly. So we will break the ties arbitrarily. Okay, so this is the first step. Select two departments which has the largest weights. Then to these two departments, we will represent these two departments by nodes like this. We will make examples. I will show you. Okay, so one department here and another department here, and we will connect these two with an edge, which means that we want these two departments to be adjacent to each other. Okay. Then we will select the third department. Based on the sum of the weights relative to the two departments. Okay, so there are a number of other departments. We will look each one of these departments one by one, and we will find their weights with these two departments. Let's say this is department 1 and this is department, let's say 5. Okay, so there are departments 2, 3, 4, and etc. other departments. So we will look at, for example, department 2's weight with 1 and 5, and we will find the sum of these weights. And for 3, again, we will find the sum of the weights, and we will do this for every one of them. And then we will identify the department which has the largest sum with the already existing or already included departments. Then we will select this department and place on the graph, and we will connect these. Then, starting from the fourth department, again we will select using the same criteria. We will find the sum of the weights with already included departments, and we will select the one which has the largest weight. After selecting a department, we will place or add these departments to the graph in order to maximize let's say we will include it into a phase of the graph in order to maximize the total or the sum of the weights. Okay? So then the question is, what is a phase? A phase in a graph, let me include one more department here. Let's assume that department 2 is also included, and we connected this with the existing departments. Now this is a graph. Okay? So an area enclosed or bounded here between 1, 2, and 5, this is a phase. Okay? And also the outside of the graph, let me show you, the outside of the graph is also mentioned or stated as a phase. So for this graph, we have this phase and this phase. So we have two phases. But let's assume that I have another department included, which is department 4. Okay, and it is adjacent with 2 and 5, let's say. Then in this graph, and also let's say that this is also adjacent to 1. Okay, then we have this phase 1, this phase 2, this phase 3, and this phase 4. Okay, so all the bounded regions, this one bounded, this one bounded, and this one bounded, plus the outside of the graph are named as phases. So whenever we select a department, we try to place that department in one of these phases, and by doing this, we try to maximize the weight. So the example will be helpful in understanding. Consider this example. We are given a relationship chart with weights. So these weights shows the relationship between the departments. These are departments 1 up to 5 and departments 1 up to 5. And then instead of the letter ratings A, E, and etc., we replace them with such weights. So a larger weight means a more relation between the departments. Okay. Now, according to the graph-based approach, the first step is to construct the graph. And in constructing the graph, the first step is to select two departments, okay, with the largest weights. And when you look at this relationship chart, the largest weight is 20, which is the weight between departments 3 and 4. So we select these two departments 3 and 4 and we connect them with a link. So a direct link between two departments means they will be adjacent in the final layout, in the block layout. Okay. By the way, this matrix or this table is given in this way because it's symmetric. So it means that if the relationship between 1 and 2 is 9, then the relationship between 2 and 1 is also 9. So these numbers here are not given because they are equivalent to these upper triangle. Then the next step is to select the third department. Okay, so we already selected the first two departments, which are departments 3 and 4, which has the largest weight. Now we will include the third department. And while including this third department, we will look the other departments. The remaining departments are 1, 2, and 5. So we will consider each one of them one by one. So department 1, we will look, for department 1, we will look its weights with the already included departments 3 and 4. We will find their values, weights, and we will add. So for department 1, the total weight is 8 plus 10. So it will be 18. Okay. So we are not adding all weights. We are only adding the weights with already selected departments. Okay. Now for department 2, again look at the weights of department 2 with already selected departments 3 and 4. And the total weight is 25. Okay. And now I need to consider the weight of department 5 with 3 and 4. But this part is empty here. Where do I find those values? Basically from here. I need to look at the weight of department 5 with department 3, which is this one. And also I need to look at department 5, the weight of department 5 with 4, which is this one. So it means that the weight of department 5, the sum of weights of department 5 between 5 and 3 and 5 and 4, it is 2. Now I calculated the sum of the weights for the remaining departments and the largest one is 2. Okay? So I'm selecting 2 and I am placing 2 into the graph. Initially I already included 3 and 4. Now I'm going to include 2. So basically if we have just 3 nodes, it will be just a triangular shape. Okay? So then I connect this new department to the existing departments by direct links. And also the numbers on these links represent the weights of the departments. Okay, the weights in between the departments. So the next step is to select the fourth department to include in the graph. Okay, and which departments are remaining? Remember, we already selected departments 2, 3, and 4. So these are already included in the graph. So I'm going to select either 1 or 5. And in order to select 1 or 5, I need to calculate their weights with the already selected departments. So for department 1, the weight of department 1 with 2, 3 and 4 are these three values, 9, 8 and 10. Okay? And for department 5, the weights between 5 and 2, 5 and 3 and 5 and 4 are given here. And I need to calculate their sums. 9, 8 and 10, so it will make 27. 7, 0, 2, it will make 9. So I will select the largest one, which is department 1, sorry. Okay, department 1 is selected, and the question is, where should I place department 1? Basically, remember, in this shape, forget about this department 1 now. What do we have? We have department 2, 3 and 4. So what are the faces? Let me sketch you. So the shape is a triangular shape. We have 2 here, 3 here and 4 here. Okay, what are the faces? One face is here, another face is here. So we are going to place department 1 either to here or to here. And if we place it to here, it can be adjacent to 1, 3 and 4. So we can sketch direct links between them. Okay? And also, instead of placing inside, if we place it outside like this, again we can sketch direct links between 1, 2 and 3. So an indirect link means something like this. For example, in this shape here, if we have a department, let's say 6 here, okay, then can we connect this department 6 to department 1? We cannot, because in order to connect it, it crosses another link. Whenever a department crosses another link, it means that it cannot be connected directly. So you can think about other alternatives. Okay, can I connect it from this side? No, because this time it crosses this link. Can I connect it from this side? No, because it crosses this link. So it means that there is no way to connect department 6 and 1 directly, because in each case it crosses one of the links. But at this stage here, if you place department 1 either inside or outside, you can connect it to all three existing departments without crossing any links. Okay? So both of them are okay in this case. But we want our shape to be as compact as possible. So when you include the department into the shape, inside the bounded region, the shape becomes more compact. But when you include it to outside, it expands. Okay? So that's why we always try to place a department inside the bounded region. Okay? So in this case, we select to include department 1 into the closed region, and then we connect this 1 with existing departments, and we sketch the direct links in between and write the weights onto the graph. Okay, so this is the end of this step. Okay, the final department that remains is department 5. Okay? So we already included department 1, 2, 3 and 4. The remaining department is 5. There is nothing to select. Okay. Now the question is to place this department 5. Where to place it? Let's consider the current situation. We already placed departments 1, 2, 3 and 4 in such a shape. And what are the faces of this shape? The red dots here shows us the faces. So we can include department 5 to any one of these faces. Then we need to select one of these alternatives. And in order to do this, we need to calculate the sum of the weights. Okay, how? Let's assume that we include department 5 to here, inside here. Then, with which other departments can I have direct links? Let's consider. Okay, so between 2 and 5, I can have a direct link because it's not crossing any other link. 5 and 1, I can also have. 5 and 3, I can also have a direct link. The question, can I have a direct link between 5 and 4? And the answer is no, because even if you go this side or this side or this, even if you go in this way or in this way or in this way, in each one of these, you cross another link. When you cross a link, it means that it's not a direct link. Okay, so if we place department 5 to this face, then we will have a direct link between 5 and 1, 5 and 2, and 5 and 3. And for this one, we go to the relationship chart and calculate the total distance. So what do we do? Since there is a direct link between 1 and 5, we include this weight. 5 and 2, then we include this weight. And 5 and 3, we include this weight. And we take their summation, and their summation is 7. Okay? So if we include department 5 into this shape, into this phase, the total sum of the weights is 7. Okay, what's the next alternative? Is to include department 5 to, let's say, here. Then we will have direct weights between 1, 3, and 4. And in that case, which of these weights will be used? 1 and 5, which is this one. 5 and 3, which is this one. And 5 and 4, this one. And this summation is 2. Okay, then we have another alternative is to include 5 to this phase, and then we will have direct links between 1 and 5, 5 and 4, and 5 and 2, and we will include this 0 here between 1 and 5, 7 here between 2 and 5, and 2 here between 4 and 5, and the weight will be 9. Okay, so we considered 3 of the faces, and there is one more, which is having department 5 here in the outside of the graph. And in that case, we may have a direct link with 2 because it's not crossing any one of the links. Then we may have a link from 5 to 3 because it's not crossing. And also we may have a direct link between 5 and 4 because it's not crossing any one of the links. So sketching this last one from here or from here does not make a difference. It means that 4 and 5 will be adjacent. Okay? And when we do this, by the way, when I say it doesn't make a difference, it doesn't make a difference in terms of the weight that we are going to calculate, but it may affect your final layout because we will transform this block layout, this graph into block layout. And while transforming it, when you sketch it in this way or in the previous way, you may end up with a different block layout. And this is how you can generate alternative block layouts, in fact. Okay, you can try by yourself if you like. And now, what's the total weight? So there's a direct link between 5 and 2, 5 and 3, and 5 and 4, and the total weight is 9. Okay, so among these 4 faces, we will select the one which has the largest weight, and the largest weight is 9, as you see, and it appeared in 2 cases. And which one of these should I select? According to algorithm, you will select one of them randomly. Okay, either if you like, you can place department 5 to here, to the outside, or you can place it to this face here. And randomly we select to place it to here. Okay? And we will proceed in that way. Now from this graph, we need to convert it to a block layout. And in fact, the block layout is basically sketching rectangles to represent departments, okay? And in fact, we sketch these rectangles maybe depending on the sizes of these departments. If the size of a department is larger, then we represent it with a larger block. If the size of a department is smaller, we represent it with a smaller block. Okay? So this rectangular shape here in this slide is the block layout. Remember, our graph is this one here. We have nodes 1, 2, 3, 4, and 5, and we have the links in between them. Okay? The links are also seen. Remember, the links represent the adjacency of these two departments. Okay, there is a link between 1 and 2. Then it means that the department that represents this 1 in the block layout and 2 should be adjacent. And adjacent means that, okay, this rectangle here or the square here is department 1. And this rectangle here is department 2. If they share a common side, it means that they are adjacent. Okay? So here you see 1 and 2 are adjacent because they share a common side. Again, department 2 and 3 should be adjacent according to our link. And you see they share a common side. It means that they are adjacent. The adjacency does not require to share the whole side to be common. If a portion of the side is common, then they are adjacent. For example, consider this side, department 2 and department 5. Okay, so according to our graph, there is a link in between. They need to be adjacent. And if you look, this side here between 2 and 5 is adjacent. Look at 2 and 4. Department 2 and 4 must be adjacent because of this link. And in order to have that adjacency, this department 4 has a weird shape. You see? It is something like a U. In real life, maybe it is impossible to have, or it's not realistic to have such departments. But still, if you want adjacency between departments 4 and 2, then you can satisfy it. You see, this side here of the two departments are shared, and it means that they are adjacent to each other. So whenever you have a graph, it is easy and it's always possible to construct a block layout satisfying all these adjacencies. Again, let's have a look at this department 1. According to our graph, it must be adjacent to 2, 5, 4, and 3. And when you look at this shape, you see it's adjacent with 2 through this side. It's adjacent with 5 through this side. It's adjacent with 4 through this side. And it's adjacent with 3 through this side. So all adjacencies of the graph are satisfied by the block layout. Okay? This is how we construct the block layout from the graph. Graph-based construction algorithm was one of the algorithms. And as I said, after you come up with final block layout, you need to calculate its score. But since it requires adjacency-based scoring, we will learn it later on, and we will be able to calculate it later on. Okay, at this stage, since we didn't learn it, we didn't talk about how to calculate it. Now let's consider an alternative approach for designing the layout, which is called systematic layout planning. Systematic layout planning consists of basically 10 steps, and these 10 steps are divided into 3 parts. The first part is the analysis part, the second part is the search part, and the final last part is the selection part. Okay, in the first step, or in the first part, which is analysis, what we do? We collect the necessary data about the activities. So what are these data? For example, the from to charts, the flow of materials, information, and etc. Okay, so basically the from to chart, and the activity relationship, which may include quantitative as well as some qualitative aspects between the departments. So we collect the necessary data to construct these from to charts and activity relationship charts. And using the information that are included in these charts, we construct the relationship diagram. So we will talk about these steps in detail in the following slides, and we will talk about what's the relationship diagram, for example. So don't be confused. This is just the general steps. First, we summarize the whole procedure, and then we will talk about each one of these steps in the following slides. Okay? After collecting the data, we constructed from to chart and activity relationship chart, and using this information, we construct the relationship diagram. Into this relationship diagram, we include the space requirements of each of these departments, and we also know how much space we have, the available space. And using these information, we construct the space relationship diagram. Okay, from relationship diagram, we have the space relationship diagram. If there are some practical limitations, or if we need to modify our considerations, we do those at this stage, and then we develop some layout alternatives. So this is the search phase of the systematic layout planning. And at the end of the procedure, we have a number of layout alternatives. We evaluate these alternatives and select the best one. All steps of the systematic layout planning are also listed here. After collecting the data and activities, we come up with the flow of materials, the from to charts, activity relationship diagrams. Using these, we generate relationship diagrams. Then we determine the space requirements and we collect the available space. Using these, we generate the space relationship diagram. If necessary, we modify our considerations. We check the practical limitations and consider those, and develop a number of layout alternatives, and we evaluate these alternatives and select the preferred design. Then where do we get the necessary data? The necessary data is collected from product design, process design, and schedule design. From product design, we have information about the components, parts, drawings, and etc. Okay? So we use this information. In process design, for each part that are necessary in production, we have the make or buy decision. Either we are buying them from outside suppliers or we make those parts inside our facilities. Then for each one of these, what are the required processes? Okay, we know this from process design, and also we know the sequence of these processes. And using this sequence of processes, we can calculate or we can construct the from to charts, from which machine to which machine, from which department to which department we make a move, we make a transfer. And the thing is, okay, we know from which department to which department there is a movement, but how many parts will be moved? And that data comes from the schedule design. Okay, we have the demand forecasts, production amounts, and the number of machines required, so that using this data, combining it with this process design and combining it with the product design, we can construct from to charts or activity relationship diagrams. Then we construct the flow of materials from two charts. Okay? Basically, we talked about the from two charts. An example is something like this. For example, from the raw material inventory, the number of parts or materials that are transferred in a certain amount of time is 16. From raw materials to drill, it's 22, and etc. Okay, so we construct such a from two chart using the product process and schedule design data. Then if there are some qualitative aspects, okay, or we want to represent these quantitative aspects in this way, we can generate these activity relationships. Again, we talked about this in our previous lectures. Basically, we represent the relationship between each department or each machine with one of these key letters, which indicates absolutely necessary, especially important, important, ordinary importance, unimportant, and undesirable. Having these from two charts or activity relationship diagrams, we construct a relationship diagram. And the relationship diagram is easy to construct. Basically, we represent each one of the departments or each one of the machines with a node in this shape. These circular colored circles represent the departments. Okay. Then looking at, for example, into the activity relationship diagram, we link these departments with each other. And depending on the relationship between them, the weight of the link or the number of links is changed. For example, for an A relationship, we use 5 lines. For E relationship, we use 4. For important, for I, we use 3. For O, we use 2. And single, and if two departments are undesirable, then we use an waved line. Okay? So, how do we construct this relationship diagram? We look at our activity relationship diagram. Again, we select two departments, and then we place these two departments into our figure. And depending on the relationship between these two, we represent the link in between them with the number of lines that represent the relationship. So in this figure, if you see, between this shipping and receiving area and stock rooms, there is an A relationship. That's why we represented the link with 5 parallel lines. And this means that, in fact, these two departments need to be closer to each other. There is a strong relationship between them. They need to be closer. By the way, this is not our final block layout. This is just a representation, and by looking at this representation, we will understand that which departments should be closer to each other and which departments should not be closer to each other, and then we modify their places and come up with the block layout. Okay? Similarly, if you see between the offices and the locker room, there is an X relationship. It's undesirable to have these two departments side by side. Again, we see this in our graph. So we will place these two departments in, let's say, far away from each other. So how to draw such a relationship diagram? As I said, the relationships between the departments shows us the proximities between the departments. How close should they be? If two activities or two departments have a relationship, then we want them to be located adjacently. If two activities have X relationship, then we want them to be located apart from each other. Okay? and we will obtain our final relationship diagram by trial and error. Okay, we will sketch. If we are not happy, we will sketch an alternative one. If we are not happy, we will sketch an alternative one. When you consider the previous alternative location of the departments, it is not the best layout because two departments with X relationship was adjacent, and two departments with an A relationship was far apart from each other. So we don't like such a layout, so we need to change it. Okay? By trial and error, we end up, or we come up with our final design. The next step is to determine the amount of space to be assigned to each activity, which means that determine the space requirements. And how to do this? In fact, there are alternative, or there are different methods to come up with the space requirements of each department. We will talk about later. And this is the fourth step. And the fifth step, okay, is to understand, or is to learn the available space. And depending on this available space, if the total space requirement of the departments are more than your available space, then you need to modify the space requirements of individual departments to fit into your available space. In the sixth step of the systematic layout planning, we construct the space relationship diagram. Basically, we already have the relationship diagram. Into this relationship diagram, we include the space requirements of individual departments, as it's shown in this figure. So this department here requires a larger space, which was offices, for example, and this department requires a smaller space. Then we include all of them into the relationship diagram. To have the space relationship diagram, you see step by step we are moving towards a block diagram. The next step is, if there are some necessity, modify the considerations, modify the space relationship diagram. Also, if there are some practical limitations, okay, again, we need to consider those practical limitations at this stage. Sometimes, for example, you want to place a department to one side of your facility. For example, you want to, in your block diagram or space relationship diagram, you show your offices to be on one side of the layout, but basically, due to the physical space, that side will not have any windows to the outside because there are large, let's say, mountains or etc. So you don't want your offices without any windows. So this is the practical limitations. It means that you need to change the location of your offices to the other side and modify your space relationship diagram accordingly. Okay, we do this to obtain alternative layouts. The next step is to develop layout alternatives. As I said, having the same space relationship diagram, different persons, different people may end up with different block diagrams. The space relationship diagram does not tell you the final solution. It just shows you the sizes of the departments and the relationships between these departments. In order to satisfy these departments, you may end up with different layout alternatives. Look at this. Okay, so in this first alternative, we have a more square-like shape. In the second one, we have this square-like shape, but it's transposed. In the third alternative, it's more rectangular. On the other hand, the places and the adjacencies between the departments are different here, whereas it's different in the second shape. And you see department 9 here is square shaped here, but it's rectangular here. Again, department 7 is square here, but it's rectangular here. Okay? And also, if you don't like such rectangular shaped departments, which is very long but narrow, you can use alternatively this one. You see, it's a better looking shape. But in this alternative, department 9 is a different shape, or also the department 5, it is L-shaped here, but here department 5 is a rectangle. You see, there are alternative layouts. Not only the adjacencies, but also the shapes of the departments, their positioning and etc. are different, and you need to select, evaluate these and select one of them. Final step of the systematic layout planning is to evaluate those alternatives and select one of them. Basically, we can consider quantitative or qualitative based approach for evaluating alternatives. We can calculate adjacency based scoring, the so-called, or distance-based scoring. We will learn about this in the next video tutorial. Okay? Or we can consider some qualitative measures, because they are also important. Other than being adjacent to each other or being close to each other, we also should consider the flexibility of the layout. Is it possible to adjust this layout for further changes? Uncertainties in the future. Okay, we should consider managerial considerations. We should consider change to the original layout, etc. Okay, so these are some qualitative measures, and they are also important. Okay, so these are the 10 steps of the systematic layout planning. Basically, in this video lecture, we learned about alternative approach for layout planning. We learned about graph-based construction algorithm, and we learned about the steps of the systematic layout planning. In the next video lecture, we will talk about algorithmic approach for layout planning.